the checker-shadow illusion. Here is a checkerboard. Square A is dark gray. Square B, sitting in a patch of shadow cast by a cylinder above it, is obviously lighter. You can see it plainly, right now, without any effort at all. Now, a professor named Edward Adelson takes a piece of paper, cuts two small holes in it, and places them over the board so that only those two squares are visible, stripped of every surrounding cue. They are the exact same color. Identical. And your brain, even now, even knowing this, will not let you see it. Edward Adelson was a professor of vision science at the Massachusetts Institute of Technology when he designed this demonstration in 1995 and published it in a teaching document that became one of the most reproduced images in all of visual neuroscience. It was not designed as a trick. It was designed to show precisely what the visual system is actually computing, which, it turns out, has almost nothing to do with what is physically in front of your eyes. The impossibility here is total. Two regions of provably identical luminosity, measurable with any photometer, any screen color picker, any piece of gray construction paper you care to cut, appear as dramatically different shades to every human observer on Earth. The illusion does not weaken with knowledge. Adelson himself, the man who designed the image, cannot override it. You can print it out, cut out the squares, place them side by side, confirm they match, then return them to the board. And the illusion immediately reappears. Your brain will not accept the evidence of your own experiment. Here is why. The brain is not measuring luminance. It is estimating surface reflectance, calculating what color a material would appear to be under neutral lighting by subtracting its internal model of the shadow falling across it. This computation is called lightness constancy, and it is the same mechanism that makes a white piece of paper look white in a dim room and a black piece of coal look black in blazing sunlight. Dale Purvis and colleagues at Duke University confirmed in 2004, publishing in the Proceedings of the National Academy of Sciences, that this correction system is not innate but learned, calibrated over a lifetime of experience watching how light and shadow behave in the real world. Artist and vision researcher Bo Lotto took this further in a series of public installations, demonstrating that the identical color illusion can be completely flipped, made to reverse its appearance entirely simply by changing the contextual frame around the squares, with no alteration whatsoever to the squares themselves. Neuroimaging studies have since shown that the visual cortex performs this reflectance calculation before conscious perception, meaning the correction happens below any level you can voluntarily access or override. Cross-cultural testing has found that the illusion is universal across human populations, though its strength varies slightly. People raised under consistent overhead lighting show somewhat stronger responses, suggesting experience continues to tune the system throughout life. The mainstream explanation for all of this is genuinely compelling. The brain evolved to recognize objects under variable lighting conditions. Without lightness constancy, a banana would appear to change identity from morning to afternoon to evening every single day. The correction system is a feature, not a bug. It gives us stable, reliable perception of a world that is lit differently from one moment to the next. Adelson himself has written that the checkerboard shows the visual system working correctly, solving a legitimately hard problem with impressive efficiency. But here is what that explanation quietly steps around. If the system is working correctly, then what you see is not reality, not an approximation, not a convenient simplification, a computation, a decision your brain made about what the world probably looks like, delivered to your consciousness in place of the raw data. Donald Hoffman at the University of California Irvin has spent decades building the case that human perception did not evolve to see reality accurately. It evolved to see fitness-relevant information, which is a different project entirely. If the checkerboard is not a special case but a demonstration of normal operation, you have never once seen the actual light that reached your eyes. You have only ever seen your brain's best guess. And some researchers now ask, is there a version of the world that exists independently of your brain's corrections? And have you ever, in your entire life, had access to it? From that still image and its impossible squares, we move to something three-dimensional. A face your brain will not let you see correctly, even when the people who cannot be fooled turn out to be the ones we least expect. The hollow face illusion. Take a mask of Charlie Chaplin's face. Turn it around so you are looking at the inside. The hollow side, a bowl-shaped cavity pressed into plaster. Hold it up and watch as it slowly rotates. For a few frames, you see what it actually is: a concave depression, shadow pooling in the center, light catching the outer edges. Then your brain makes a decision. The hollow face pops outward. It grins at you. You are at this moment looking at a hole, and you are completely incapable of seeing it as one. British psychologist Richard Gregory formally demonstrated this effect in 1974 as part of his broader research into what he called top-down visual processing, the way that prior knowledge and stored expectation actively shape raw perception. He used a rotating hollow mask to argue that the brain's model of what a face should look like is powerful enough to override the actual geometry arriving at the retina. The effect became one of the most studied demonstrations in cognitive neuroscience, and in the decades since, it has revealed something far stranger than Gregory may have anticipated. The core impossibility is this: the visual system receives geometrically correct information that the face is concave. The shadows confirm it. The highlights confirm it. The perspective confirms it every single frame of the rotation. The brain rejects all of it. It replaces the correct interpretation with a false one because it cannot reconcile the concept of a hollow human face with its stored model of how faces work. Most people cannot override this regardless of how hard they try. It is not a failure of attention or intelligence or concentration. The brain simply will not process a hollow face as hollow. In 2009, researchers at the University of Edinburgh and University College London, including Philip Bressler and colleagues, published a finding in NeuroImage that stopped many researchers in their tracks. Patients with schizophrenia are largely immune to the hollow face illusion. They see it correctly, as concave, in cases where neurotypical observers simply cannot. The immunity is linked to impaired top-down processing, the same neural mechanism that is believed to contribute to hallucinations in psychosis. A 2010 study by Dima and colleagues, also published in NeuroImage, used functional magnetic resonance imaging to confirm the difference. Schizophrenic participants showed measurably different patterns of frontal cortex activation during the hollow face task, specifically in the region responsible for applying the corrective signal that neurotypical brains impose. The correction was absent, and the absent correction produced the accurate perception. The illusion, it turns out, is strengthened by familiarity. A hollow mask of a face you know well is harder to see correctly than a hollow mask of a stranger, as if personal knowledge reinforces the override. Drug studies have added another dimension: psilocybin, which is known to temporarily disrupt top-down predictive processing, produces partial resistance to the hollow face effect, allowing subjects to perceive the concavity more readily. And the effect persists in live physical demonstration even when the viewer is holding the mask with their own hands and can feel with their fingertips that it is hollow, while their eyes continue to insist that it is not. The mainstream explanation holds together reasonably well. The brain uses statistical priors, models built from a lifetime of experience, to interpret ambiguous sensory input. In the real world, concave human faces essentially do not exist. A hollow face is so statistically improbable that applying the prior expectation of convexity is, in almost all circumstances, the rational move. This is Bayesian perception, making the most probable inference given everything you know. The hollow mask is an edge case that reveals the mechanism, not a failure of it. But the schizophrenia data cuts somewhere the mainstream story does not fully reach. If patients with disrupted top-down processing see the hollow face correctly, and neurotypical brains see it incorrectly, then what exactly is the healthy brain doing? It is not perceiving more accurately. It is perceiving more confidently, imposing its model of the world onto ambiguous data with enough force to overwrite what is actually there. And supposedly, if that imposition is running on every face you have ever looked at, then some researchers are left asking, every time you look at a friend, a stranger, a face in a crowd, is your brain seeing them? Or is it seeing its prediction of them, updated just barely enough to pass? The hollow face shows your brain refusing to release a perception it trusts. Now, hear what happens when it goes one step further, not merely refusing to correct, but generating a perception that exists in neither of the inputs you give it. The McGurk effect. A man on screen is clearly mouthing the syllable "gay." The audio track is clearly playing "ba." You watch them together, and you hear "da," a sound contained in neither the video nor the audio, a phoneme assembled by your brain from two contradictory sources and handed to you as finished reality. Close your eyes now and listen without the image. Ba. Open your eyes again. Da. Your brain is building sounds that do not exist, and it is doing it so completely that knowing the trick does not stop it from working. Harry McGurk was a developmental psychologist at the University of Surrey in England, studying how infants learn to perceive speech when in 1976 a technical error during an experiment caused the audio and video tracks to be mismatched. McGurk expected the team to simply hear what was on the audio. Instead, they heard something neither track contained. He and his research assistant John MacDonald published the finding in the journal Nature in December of 1976 in a paper titled Hearing Lips and Seeing Voices, a paper that has since been cited more than 3,000 times across dozens of languages and research traditions. McGurk himself, it is reportedly said, could never hear through the effect after publishing its mechanism. He had written the explanation and could not apply it to his own experience. The impossibility sits right there. The brain receives audio input of bay and visual input of gay and synthesizes day, a phoneme that lives in neither stream. This is not mishearing one input or the other. It is the generation of a third option, created wholesale by integrating two conflicting sources. The effect persists with complete knowledge of the trick. It persists when you are told, syllable by syllable, exactly what sounds are in the audio and exactly what movements are in the video. Some researchers who have studied the McGurk effect professionally for years still cannot hear through it in real time. A 2013 study by Beauchamp and colleagues, published in the Journal of Neuroscience, used functional magnetic resonance imaging to locate the primary integration site, the superior temporal sulcus, a region responsible for merging audio and visual speech signals before they reach conscious awareness. The critical detail is timing. That integration happens approximately 250 milliseconds before conscious perception. The invented phoneme arrives in consciousness as a finished product, with no record of the conflict that produced it, no flag, no asterisk. Research by Massaro and colleagues framed the mechanism precisely. The brain treats the McGurk conflict as a probabilistic inference problem, calculating the most likely phoneme given both inputs simultaneously and producing a result that satisfies neither input independently but is statistically coherent given both. The effect is stronger in adults than in children, and stronger in people with high audiovisual integration ability, which means it is not a deficiency of a poorly calibrated system. It is a signature of a well-developed one. People with autism spectrum disorder show a reduced McGurk effect, their brains weighting auditory information more heavily and performing less aggressive audiovisual fusion, resulting in more accurate phoneme identification in precisely this context. Cross-modal sensory integration research helps explain why. Visual lip movement carries precise timing information that ambient audio lacks in noisy environments, so the brain learned over evolutionary time to weight it heavily for speech. The synthesized phoneme is the rational output of that weighting strategy. The mainstream explanation is honest about this. Speech perception is inherently multimodal. The brain evolved in environments where lip reading provided critical additional information for parsing speech through noise. Combining audio and visual streams is not an error. It is the correct strategy, and it works correctly in the overwhelming majority of real-world situations. The McGurk effect is the cost of that efficiency, revealed only when the inputs are deliberately set against each other. But the brain does not tell you that it has synthesized the phoneme. It does not deliver the computed result with any kind of disclosure. No signal that what arrived in your awareness was produced rather than received. Every time you have had a conversation in a noisy room, every phoneme pieced together from a half-heard mumble, every word parsed through an unfamiliar accent in a crowded place. Your brain was running this calculation and handing you the output labeled as reality without annotation. Some researchers have begun to ask whether unmediated hearing exists at all, or whether every conversation you have ever had was already a construction assembled below the level you were ever given access to. The McGurk effect shows the brain adding something that was never there. What follows shows the system running in reverse, quietly, seamlessly, deleting things that are. The Troxler effect, Vienna, 1804. Fix your gaze on a single point. Hold it there, completely still, for 30 seconds. The objects around it, the ones sitting just outside the center of your attention, begin to fade. Not gradually and gently, the way things dim when a light goes out. They fade, and then they vanish, cleanly, while you are watching. Not because you stopped paying attention, not because you looked away. Your brain classified that information as stable, decided it was no longer necessary, and deleted it. The gap it left behind was then covered over, seamlessly, with something it invented. You never saw the seam. Swiss physician and philosopher Ignaz Paul Vatel Troxler first described this in 1804, presenting his findings on attention and visual fixation at a symposium in Vienna. He observed that sustained fixation on a peripheral stimulus caused it to fade and disappear entirely, then reappear the instant the eye moved. The phenomenon was treated as a curiosity for well over a century before 20th century neuroscience identified what was actually happening. Neural adaptation in the retinal ganglion cells and the lateral geniculate nucleus provides the first stage, but the suppression goes deeper than simple fatigue. A 2006 study by Simons, Laris, and colleagues published in the Journal of Vision confirmed that the disappearance involves active cortical gating. The visual cortex signals downstream regions to actively reduce the weight assigned to stable peripheral inputs. The fading is not the absence of processing, it is a decision. The brain compensates for this under normal conditions through tiny involuntary eye movements called microsaccades, made approximately 70 to 90 times per minute. Each microsaccade refreshes the retinal image and resets the suppression clock, preventing wholesale fading of the visual field. When microsaccades are artificially suppressed using experimentally stabilized images, a technically demanding procedure, the central visual field itself begins to fade. The entire scene progressively disappears from the edges inward. The world goes out. What the fading leaves behind is equally important. The brain does not simply delete a region and leave it dark. It fills the gap with the texture and color of the surrounding area, a process called perceptual completion, covering the absence seamlessly without any notification that it has done so. This same mechanism underlies the blind spot. Every human being has a natural hole in their vision where the optic nerve exits the retina, and in a lifetime of seeing, most people have never once perceived it as a hole because the brain fills it in automatically, continuously, without ever mentioning that it is there. The mainstream view of all this is straightforward and worth taking seriously. Neural adaptation is a fundamental efficiency feature of every sensory system we know of. Constant processing of stable, unchanging stimuli would consume enormous neural resources and drown out the signals that actually carry useful information. Movement, change, new threats, new opportunities. The visual system evolved to report change, not continuity. Troxler fading is the system correctly deprioritizing static background information in favor of dynamic foreground. The filling in ensures the gaps are covered and the working model of the environment remains functional. But what this means in practice is that your visual field, at any moment you care to examine, is partially live and partially constructed. The brain is filling in regions that have faded with an informed guess based on surrounding context. Invisibly, seamlessly, without any indication that a guess was made. The microsaccades that prevent this from happening to your entire visual field are entirely outside your voluntary control. You cannot govern your own visual refresh rate, which means some researchers are left asking, how much of what you see right now is current data, and how much is the last version your brain decided was probably still accurate, and how would you know the difference? From Vienna and the disappearing periphery, we travel to the Scottish Highlands in 1834, where a man stood beside a waterfall and discovered that the brain does not only delete motion, it manufactures it. The Waterfall Illusion. Falls of Foyers, Scotland, 1834. Stand at the edge of a waterfall for 30 seconds and watch the water cascade downward. Then look at the rock face beside it. The rocks are moving, upward, visibly, trackably, in the opposite direction of the water you were just watching. You know they are not moving. They have never moved. But the motion is entirely real to you, and you cannot make it stop simply by knowing why it is happening. Robert Adams described this experience at the Falls of Foyers in 1834 and published his account in the London and Edinburgh Philosophical Magazine, noting that the apparent upward motion of the cliffs was impossible to suppress regardless of how complete his understanding of the situation was. What Adams may not have known was that someone had already described the same effect more than 2,000 years earlier. Aristotle documented it in Parva Naturalia around 350 BCE, observing that after watching a river flow, stationary objects appeared to move in the opposite direction. This makes the waterfall illusion the oldest documented optical illusion in recorded human history, described by two of the most careful observers in Western intellectual tradition, separated by more than 22 centuries, unable to explain it. The impossibility is precise. The rocks are stationary. The retina is receiving a flat, unchanging image of them. No motion signal exists in the input. And yet the visual cortex is producing a conscious experience of upward movement, real, sustained, trackable, using the same neural architecture it uses to perceive motion that is genuinely occurring. In the 1960s, neurophysiologist Horace Barlow and colleagues identified direction-selective neurons in the mammalian visual cortex, cells that fire specifically in response to motion in one direction and are actively suppressed by motion in the opposite direction. The motion after effect arises when one set of these directional neurons becomes fatigued by prolonged stimulation, and its opponent population becomes relatively more active in the silence that follows. The imbalance is read as motion by higher visual areas. The program runs. The rocks move. In 1997, a team led by Tutel and colleagues at Harvard Medical School published a study in Nature Neuroscience using functional magnetic resonance imaging to examine what happens in the brain during a motion after effect. The motion area, V5, also known as MT, activated during the after effect, the same region that fires when you watch an object that is actually moving. No physical motion was present. The brain was running the motion perception program on empty input and producing a conscious experience indistinguishable to the observer from the real thing. The effect transfers across eyes. Adapting with the left eye produces after effects perceived by the right, confirming that the mechanism operates at the cortical level rather than at the retina. And motion after effects turn out to be only one version of a broader pattern. Analogous after effects have been documented for color, tilt, size, face identity, emotional expression, and perceived gender, suggesting the fatigue and rebound architecture is a general feature of perceptual systems rather than a quirk specific to motion. The mainstream explanation is clean and plausible. Directional selectivity and opponent processing are adaptive features that allow the visual system to detect relative motion and figure-ground relationships with exceptional sensitivity. Channel fatigue is an unavoidable byproduct of any sustained neural activity. The after effect is a brief artifact of otherwise efficient processing. It exposes how the motion system is organized through specialized, efficient channels, exactly as a well-designed system should be organized. But the Harvard fMRI data sits uncomfortably against that framing. V5 activates identically for real motion and illusory motion. At the neural level, there is no measurable difference between the experience of perceiving movement and the experience of hallucinating it. The same hardware, the same program, the same conscious output. The only distinction is whether the input was real. Neuroscientist David Eagleman at Stanford has argued that what we call seeing is actually the brain's prediction of what the world will look like roughly 100 to 200 milliseconds from now, running slightly ahead of real time to compensate for neural processing delays. In that model, motion perception is always a neural construction, never a direct readout. The waterfall after effect is the prediction running unanchored, stripped of its input, still producing the experience. And if that is the case, some researchers ask, what are we actually watching every time we watch anything at all? But manufactured motion is still, in some sense, one brain and one image. What happens when two images arrive simultaneously, one in each eye, and the brain is forced to choose between two different worlds? Binocular rivalry. Show your left eye a horizontal grid. Show your right eye a vertical grid at the same moment. You might expect to see both, some kind of merged pattern, a combination of the two. What you get instead is an election. One image wins, the other vanishes completely. not dims, not fades to the background, disappears. Then, after a few seconds, the loser returns and the winner disappears. Your two eyes are watching different worlds, and your brain is running a competition between them moment by moment with or without your permission. Charles Wheatstone, the inventor of the stereoscope, first formally documented binocular rivalry in 1838 while developing his apparatus for presenting different images to each eye. He observed that rather than fusing incompatible inputs, the visual system alternated between them. The phenomenon remained primarily a curiosity until the late 20th century, when researchers realized it offered something rare: a stimulus that stays physically constant while perception changes, which means it can be used to study the brain basis of conscious awareness itself, separate from the confound of changing sensory input. In 1996, Nikos Logothetis and colleagues at the Max Planck Institute published a landmark experiment in Nature. They implanted electrodes in macaques trained to report which image they were perceiving during binocular rivalry. The finding was striking. Neurons in the primary visual cortex, V1, the earliest cortical processing stage, continued firing for both images throughout the rivalry. Both images were being processed, but neurons in higher areas, specifically in the inferotemporal cortex, tracked only the image the animal was currently reporting as consciously perceived. The suppressed image was reaching the visual cortex. It was generating neural activity. It was simply not achieving awareness. Switching rate during rivalry turns out to be a remarkably stable individual characteristic. Measured across sessions weeks apart, it correlates with white matter connectivity in the corpus callosum, as Rumen Valev and colleagues showed in 2011. A 2016 study by Deiter and colleagues, published in Psychological Science, found that individuals with more variable switching rates scored higher on divergent thinking tasks, suggesting that the flexibility of perceptual competition may be related to creative cognition in ways not yet fully understood. Patients in the early stages of psychosis show significantly slower switching rates in rivalry tasks, as documented by Miller and colleagues in 2003 in Neuropsychologia. The competitive inhibition between perceptual states appears less efficient. In a 2005 study published in Current Biology, Carter and colleagues demonstrated that experienced meditators show greater voluntary control over switching rates than non-meditators, indicating that attentional training can measurably modify these normally automatic competitive dynamics. And continuous flash suppression, an enhanced rivalry technique in which a rapidly flickering pattern in one eye suppresses a static image in the other for several seconds, has shown something deeply relevant. Threatening stimuli, including faces and spiders, break suppression significantly faster than neutral stimuli, even when never consciously perceived. The suppressed information is influencing behavior from below the level of awareness. The mainstream explanation for rivalry is reasonable. The brain evolved to receive complementary input from two forward-facing eyes directed at the same scene. Incompatible inputs represent a situation it was never designed to handle. The competitive inhibition between neural representations is the system's best available response to an impossible input, a sustained oscillation driven by neural adaptation alternating between the two representations rather than blending them into uselessness. The alternation is correct behavior in an abnormal situation, but Logothetis' 1996 data places a weight on this explanation that it does not quite bear. V1 fires for both images the entire time. The suppressed image is being processed at the primary cortical level. It is generating real neural activity. It is simply being withheld from consciousness by a filter operating somewhere between sensory processing and awareness. That filter is choosing moment by moment what you get to know about. and the flash suppression evidence suggests the filter does not stop there. That below awareness, the suppressed information continues to shape behavior. Some researchers have begun to ask whether this filter is a special feature of the rivalry paradigm, or whether a version of it is running on everything you perceive all the time, deciding what enters the stream and what runs silently in the dark behind it. From London in 1838 to a living room in Scotland in 2015, where the same battle between two incompatible perceptions played out not in a laboratory, but on the screens of 10 million people at once. The Dress, February 26, 2015. A woman in Collieston, Scotland, photographs a dress hanging in a shop and posts it to Tumblr with a simple question: "What color is this?" Within 24 hours, 10 million people have seen it. Some see black and blue, some see white and gold. They are not in different rooms with different screens. Some of them are sitting side by side, looking at the same device. They are not disagreeing about what they think. They are receiving different perceptual experiences from identical physical input. Caitlin McNeil took the photograph that day, and it spread faster than any image in Tumblr's history. By the following morning, neuroscientist Carl Gegenfertner at the University of Gießen had already posted an explanation grounded in color constancy research. Within weeks, peer-reviewed studies were appearing. The definitive examination came from Bevel Conway at the National Eye Institute, published in Current Biology in 2017 with 1,401 participants, one of the largest individual differences studies in color perception ever conducted. The physical facts are important to establish. Gegenfertner's colorimetric analysis confirmed that the pixels of the dress image fall in a genuinely ambiguous range. The image does not contain sufficient information to determine the quote correct answer without an assumption about the ambient light source. Both perceptions are, in a strict sense, defensible inferences from the data. Conway's study found that 57% of participants saw the dress as blue and black, 30% as white and gold, and 10% as blue and brown. The strongest single predictor of which color a person perceived was their habitual daily light exposure. Self-identified morning people, who wake early and begin their days under cool natural dawn light, were significantly more likely to see white and gold. Evening. Preferring individuals were significantly more likely to see blue and black. The brain assumes a lighting source and subtracts it from the image to estimate the material's true color, what the fabric would appear to be under neutral illumination. Different assumed light sources, built up through different lifestyles and different histories of morning and evening exposure, produce categorically different results. A follow-up neuroimaging study by Schlafke and colleagues, published in Cortex in 2015, found that white and gold perceivers showed greater activity in higher visual areas involved in illumination estimation. Their brains were performing more top-down interpretive work on the image, working harder to assign it a light source. The neural pathway for this disambiguation includes the prefrontal cortex, which implies that higher-order factors, including attention, mood, and prior experience, influence color perception at an unconscious level before the result reaches awareness. Subsequent controlled photography established that the physical dress is black and blue. The blue and black perceivers were factually correct, but the white and gold perceivers were not hallucinating. They were performing a rational inference from genuinely ambiguous data, using a prior assembled from a different life. The mainstream explanation stands. Color constancy is individually calibrated through lived experience, and when the image lacks sufficient illumination cues to resolve the ambiguity, different priors produce different outcomes. Both groups applied the system correctly. The image simply could not be resolved by either group alone. But the dress carries an implication the mainstream account does not fully absorb. Two people sitting beside each other, looking at the same screen, are having experiences that are not merely differently interpreted, they are categorically different. For the white and gold perceivers, the blue wavelength reflecting off that fabric did not arrive in their consciousness. The physics was identical. The experience was not. Philosopher Thomas Nagel famously asked what it is like to be a bat, whether another creature's consciousness resembles ours in any experiential way. The dress asks a harder question. What is it like to be you, receiving this image, versus someone else receiving it in the same room? We have long assumed that shared stimuli guaranteed shared experience. We have never had as clear an image of that assumption failing. Some researchers now ask whether the color vocabulary we share, the word blue pointing at the same patch of sky, is pointing at the same inner experience in both of us, or whether we agreed on the word long ago and never had a way to check what was underneath it. From a photograph of a dress and the question it left open, we move inward. From the disagreement of two minds about an external object to what happens when a single mind is convinced that an artificial object is part of its own body. The rubber hand illusion. Carnegie Mellon University, Pittsburgh, Pennsylvania, 1998. Place your left hand flat on a table, then slide it underneath, out of sight. Place a rubber hand on the table surface in approximately the same position. Watch as a researcher strokes both hands simultaneously with a paintbrush. The rubber one that you can see, the real one that you cannot. After 10 minutes, something has shifted. The rubber hand is yours. Your brain has adopted it completely. And when the researcher picks up a hammer and moves it toward the rubber hand, your real hand, hidden under the table, unthreatened, flinches. Matthew Botvinnik and Jonathan Cohen were researchers at Carnegie Mellon when they published this effect in Nature in 1998 in a brief communication titled Rubber Hands Feel Touch That Eyes See. They observed that synchronous stroking of a visible rubber hand and a hidden real hand produced in the majority of participants a felt sense of ownership over the rubber hand, accompanied by a measurable displacement of the perceived location of the real hand toward the rubber hand's position. An average drift of 1 to 3 centimeters documented across their initial sample. They were not the first to suspect that body ownership might be constructed rather than fixed, but they were the first to demonstrate it cleanly in a laboratory and measure it with precision. The impossibility is physiological, not merely perceptual. The rubber hand is clearly not attached to the participant's body. Participants know this throughout the procedure. And yet the brain generates a felt sense that the rubber hand is mine. A subjective experience of ownership based solely on the synchrony of visual and tactile signals. A 2004 study by Armal and Ramachandran, published in Experimental Brain Research, demonstrated that threatening the rubber hand produced a measurable galvanic skin response. The sympathetic nervous system responded to the threat to a fake object as if it were a threat to actual tissue. Earson, Holmes, and Passingham, publishing in Science in 2004, used functional magnetic resonance imaging to locate the neural sites of rubber hand ownership, the premotor cortex, the intraparietal sulcus, and the cerebellum, the same regions that represent the genuine body under normal conditions. The effect requires synchrony. Asynchronous stroking with a delay of 500 milliseconds between the rubber hand and the real hand produces dramatically reduced ownership, confirming that the temporal match between visual and tactile signals is what drives the adoption, not mere proximity or sustained attention. Lengenhager and Blanca at EPFL Lausanne extended the mechanism to a full-body version in 2007, published in Science, projecting a participant's video image slightly in front of them and stroking the physical participant and the projected image simultaneously produced a felt displacement of the self toward the external image. Body ownership extended beyond the skin entirely. Clinical researchers have explored applications for phantom limb pain management, with some amputees showing measurable pain reduction when induced to experience ownership of an artificial limb. The illusion is disrupted in people with anorexia nervosa in a specific way. They report the ownership sensation but show no proprioceptive drift toward the rubber hand, suggesting that body boundary processing is modulated by body image disturbance in ways that have yet to be fully characterized. The mainstream explanation is coherent. Body ownership depends on multisensory integration of visual, tactile, and proprioceptive information. The brain uses Bayesian inference to determine which objects in space belong to the self. When visual and tactile signals are synchronized, the most parsimonious explanation is that they originate from the same body part. The rubber hand illusion shows the system applying this logic correctly to an unusual input. It is not a failure of body representation. It is correct behavior in an edge case designed to produce a specific result. But the physiological data goes somewhere the mainstream account does not follow. The body is responding to a rubber hand as if it were real tissue, circulatory redirection, sympathetic nervous system activation, stress response to threat. These are not high-level cognitive errors. They are physical events. The border between self and not self, the most basic, most certain boundary any organism can possess, is apparently 10 minutes of synchronized brush strokes away from being redrawn. Philosopher Thomas Metzinger argued in Being No One, published in 2003, that the sense of owning a body is itself a constructed model, not a given feature of experience. In that view, the rubber hand illusion is not the brain making an error. It is the brain doing precisely what it always does, building a model of the body from incoming signals in a setting designed to expose the building process. Some researchers now ask whether there is a real body boundary being violated here at all, or whether the boundary was always a prediction, and whether, under the wrong conditions, that prediction might rewrite itself without anyone designing it to. The rubber hand shows the brain can be convinced you own a foreign object. Now meet the system so over-calibrated it sees faces in surfaces that have never held one, and responds to them before you finish the thought. Pareidolia. Look at the electrical outlet on the wall. 2 rectangular holes and a slot below them. There is a face there. You know there is not a face there. Both of those things are true simultaneously. And what you may not know is that your brain identified it as a face, assessed its expression, and generated a partial social response to it before you finished reading that sentence. Nancy Canwisher, Josh McDermott, and Marvin Chun at the Massachusetts Institute of Technology published a study in the Journal of Neuroscience in 1997 that identified a region in the fusiform gyrus of the temporal lobe, the fusiform face area, that activates selectively in response to face-like stimuli. What they and subsequent researchers found was that the fusiform face area activates not only for actual faces, but for any sufficiently face-like configuration. 2 dots above a curved line, the grille of a car, the surface of the moon. The face detection system, it turned out, does not require a face. It requires only a configuration that resembles one closely enough to cross a threshold set apparently quite low. The timing is what matters most. The N170, an EEG component peaking approximately 170 milliseconds after a face or face-like stimulus appears, is the earliest identifiable neural signature of face processing, and it fires for cartoon faces, inverted faces, and face-like objects as well as for genuine faces. 170 milliseconds is before conscious recognition. The social response to a face precedes your awareness that you are seeing one. A 2009 study by Susilo and colleagues, published in Neuropsychologia, found that patients with prosopagnosia, Face blindness caused by fusiform face area damage still experience pareidolia, suggesting the detection system extends beyond the fusiform face area into a distributed network with multiple face-selective processing layers. Psychological research by Alice Eisen and colleagues found that positive mood states increase pareidolia. People in good moods detect more faces in ambiguous stimuli, which indicates the threshold for face detection is modulated by emotional state. The face in the crowd effect, documented by Hansen and Hansen in the Journal of Personality and Social Psychology in 1988, showed that angry faces in a crowd are detected faster than happy faces, confirming that the system is asymmetrically weighted toward social threat rather than social neutrality. Developmental research by Morton and Johnson in 1991 found that infants as young as 9 minutes old preferentially track a moving face-like pattern over a scrambled control, suggesting that at least a partial foundation for face detection is innate, predating any learned face exposure. The Mars connection is the most public demonstration of what this system can produce. In 1976, NASA's Viking 1 orbiter photographed the Cydonia region of Mars and captured a surface feature that looked, under that particular sun angle and at that particular resolution, strikingly like a human face. NASA received enough public correspondence in response to prompt an official statement. In 2001, the Mars Reconnaissance Orbiter photographed the same formation in high resolution and under more representative lighting. It was an eroded mesa. The face had been assembled entirely by the most powerful recognition system in the human brain, from shadow and low resolution and an angle of light that happened to produce the right arrangement. Physiological measurements during pareidolia, pupil dilation, galvanic skin response, heart rate, show measurable social and stress responses to face-like objects, not as strong as to actual faces, but consistent and replicable. The mainstream explanation is honest and logically sound. In social primates, rapidly identifying faces and reading their emotional content, their directional gaze, their social intent, provides immediate information about threat, alliance, and opportunity. The cost of false positives is low. The cost of missing a real face can be catastrophic. Natural selection strongly favors a detection system calibrated to over-identify. Pareidolia is the expected rational byproduct of exactly that calibration, but the physiological evidence suggests the system is doing more than misidentifying an object. It is partially socially engaging with a drain cover. The computation your brain runs when it looks at a face, assessing trustworthiness, reading emotional state, computing likely intentions, appears to run continuously on any stimulus that crosses the face detection threshold, whether or not you consciously register it as a face. Your social cognition is reportedly leaking into your experience of the inanimate world, continuously below your awareness. Stuart Guthrie at Fordham University argued in Faces in the Clouds, published in 1993, that this mechanism may be the cognitive engine beneath religious and spiritual experience, that perceiving intentional agents in natural phenomena, weather, fire, and landscape, was adaptive enough to produce a systematic tendency to populate the world with presences. In that view, some researchers ask, the perception of divine or spiritual agency in nature may not be a belief layered on top of neutral perception. It may be perception itself, the face detection architecture applied to clouds and mountains and the patterns of stars, running before belief, beneath thought, and reporting a social world full of agents who may have never been there. From faces in walls and faces on Mars, we arrive at the final item, the most fundamental measurement the brain makes, and the illusion that reveals it is not universal. The Müller-Lyer illusion. Germany, 1889. 2 lines. They are identical in length. One has arrowheads pointing inward at each end. One has arrowheads pointing outward. The one with inward arrows looks longer. you can measure them. You can mark the endpoints with a pen, slide them apart, confirm they match within a fraction of a millimeter. You can return them to the page. You will still see them as different. Now travel to the Kalahari Desert and show the same image to a sand hunter-gatherer who has lived their entire life in open savanna, under wide sky, without a single right-angle wall in their built environment. For them, this is barely an illusion at all. Franz Karl Müller-Lyer, a German sociologist and psychiatrist, published this figure in 1889 in Philosophische Studien. For nearly a century, it was treated as a clean, universal demonstration of how human perception works. Then Marshall Siegel, Donald Campbell, and Melville Herskovits ran a cross-cultural study and published it in Science in 1963, testing 14 non-Western populations alongside Western participants. The results dismantled the universality assumption entirely. Western populations showed the strongest illusion, perceiving the arrowhead in line as roughly 20% longer than the identical arrowhead outline. Populations from open habitat, low carpenteredness environments showed significantly weaker effects. Some showed almost none. The explanation they proposed became known as the carpentered world hypothesis. The brain learns to interpret acute and obtuse angles as depth cues. The corners of rooms, the edges of door frames, the receding lines of hallways. When you grow up inside right-angle architecture, your brain builds a habit of reading these angular configurations as three-dimensional space and applies that habit to two-dimensional drawings. Richard Gregory formalized this in a 1963 analysis in Nature, calling it misapplied constancy. The brain applies size constancy scaling to the flat image as if it were a three-dimensional scene, causing the arrowhead inversion to appear more distant and therefore, through the size constancy correction, larger. Developmental studies confirm that children in urban environments become progressively more susceptible to the Müller-Lyer between the ages of 4 and 12 as their brains accumulate exposure to right-angle architecture. The illusion is not innate, it is installed. A 2018 neuroimaging study by Murray and colleagues pushed the finding deeper. The primary visual cortex representation of the two lines is actually different in size. The brain constructs a physically different neural map of two physically identical stimuli, with the distortion occurring at an early, low-level stage of visual processing, not at a high-level interpretive stage that might be more amenable to correction. The error is written in before the brain ever gets to think about it. Joseph Henrich, Stephen Heine, and Ara Norenzayan's 2010 paper in Behavioral and Brain Sciences, the paper that introduced the acronym WEIRD for Western, Educated, Industrialized, Rich, and Democratic, cited the Müller-Lyer as a primary example of a cognitive phenomenon incorrectly treated as universal based on samples drawn entirely from one kind of human environment. That paper has been cited more than 8,000 times. The mainstream explanation takes all of this seriously. The carpentered world hypothesis accounts for the cross-cultural variation effectively. The brain uses pictorial depth cues it learned from its built environment. Western populations have more of that learning. The variation reflects different priors, not different perceptual abilities. The illusion is a rational misapplication of a useful heuristic to an unusual stimulus, correct behavior in the wrong context. But the WEIRD paper's implications settle into something the mainstream account does not fully contain. If a basic visual measurement, the length of two lines, one of the simplest perceptual operations conceivable, gives different results depending on the architecture surrounding you as a child, then what does that say about every other visual and cognitive phenomenon studied almost exclusively on Western university students and then labeled universal human cognition? The Müller-Lyer did not merely reveal a visual quirk. It reportedly revealed that the entire project of 20th century perceptual psychology may have been describing one particular kind of human perception, calibrated inside one kind of world, built within certain walls, and mistaking it for the kind all humans share. The sand hunter-gatherer and the Manhattan architect are not looking at those two lines differently in any superficial sense. They are, in some measurable and documented way, looking at a different version of reality. Philosopher Mark Johnson has argued that the structure of our embodied experience, the rooms, streets, and physical environments we inhabit, shapes the conceptual architecture through which we interpret all experience, including abstract reasoning. The Muller layer may be the place where that claim becomes visible. If the shapes of the walls you grew up inside determine how your brain measures lines, some researchers ask, what else about your perception of the world, the depth, the distance, the comparative weight of things, was quietly decided for you by the room you grew up in, long before you had a word for any of it? There is a line running through every illusion in this list. The checkerboard computes reflectance instead of reading light. The hollow face imposes a model instead of perceiving geometry. The McGurk effect invents a sound. The Troxler effect erases what is actually there. The waterfall manufactures motion from silence. Binocular rivalry chooses between two worlds and hides its choice. The dress sends two people identical pixels and delivers two different realities. The rubber hand erases the boundary of the self. Pareidolia fills the inanimate world with social agents. The Muller layer measures a line and gets it wrong, but only in certain cultures, built inside certain walls. The line running through all of them is this: you have never perceived the world directly. Every image, every sound, every color, every face, every line you have ever seen, it was computed, corrected, filtered, predicted, completed. The raw data is not the experience. The experience is what your brain decided to show you. After running that data through every prior it has ever built, every assumption, every environment has ever installed. You have always been living one step inside a model. The mainstream view of this is worth hearing honestly. These are edge cases, designed stimuli, unusual inputs that expose the cost of systems that otherwise perform extraordinarily well. The brain is very good at its job. Lightness constancy, face detection, multisensory integration, motion processing. These are remarkable achievements of evolutionary engineering, and the illusions are the seams you only notice at the edges. But supposedly, the seams are everywhere. The Troxler effect is running on your peripheral vision right now. The hollow face effect is running on every face you look at. Color constancy is operating on every surface in the room. Pareidolia is processing every ambiguous contour in your environment. The McGurk synthesis is running on every conversation you have in noise. These are not special conditions deployed only in laboratories. They are standard operations running continuously, mostly invisible, occasionally legible. The philosopher David Hume wrote that we have no access to the world as it is, only to the impressions the world makes on us. These 10 items are what it looks like when the impression machine becomes briefly, uncomfortably visible. Most people look at optical illusions and see party tricks, curiosities, something fun to share. They accept the label illusion and return to the comfortable assumption that normal vision is something else, direct, accurate, unmediated, a window rather than a construction. You watch this far, which means you already sense what that implies. If these are the illusions, what is the rest? This channel exists for the people who stay with that question. Hit subscribe, because this is one page of a very long archive. And go to the comments with this: of these 10, which one changed something? Not the most dramatic, not the most technically impressive. The one that landed. The one that made the model feel for a moment like a model. Tell us which item and tell us why. The floor is yours. You began with a checkerboard, 2 squares, identical gray, one brain unable to see them as the same. Somewhere between that checkerboard and this moment, something shifted. Some assumption about what your eyes are doing when they open in the morning and what they actually owe you. The ancient answer was simple. The world comes in. The neuroscience answer is stranger and in some ways harder to live with. The world begins to be assembled every moment from priors and predictions and patches over the gaps, delivered without credits and without a single note that any of it was built. Every illusion in this list is a window into that assembly. Look through enough windows and you start to see the factory. You were never just seeing. You were always building.